So my name is Maurice Beek. I'm talking to you from Italy. So for me, it's about to become evening, but I know that for others, they are in different time zones. So welcome everyone in this session on probabilities. So for the speakers, please, we have here three full presentations and two short ones. So we have a little bit different timing. So the first one is a full presentation, so 20 minutes. In total, please try to present in about 15 minutes, leaving some time for questions. And questions can be posed in the chat, or one can raise his hand or her hand. And then maybe we can repeat the question live and get the answers from the presenters. So the first talk will be given by Đorđe Žikelić. Sorry if the pronunciation is not exactly good. And it's on lexicographic proof rules for probabilistic termination. So please share your screen and.
Thank you. Okay. I will start sharing my screen. Do you see it?
Yes, I do.
Okay, perfect. So, hello, my name is Đorđe Žikelić, and I will talk about the work on lexicographic proof rules for probabilistic termination. This is a joint work with Krishnendu Chatterjee, S. Angokharshadi, Petr Novotny, and Jerzy Zarewotsky. So probabilistic programs extend classical programs with randomization, and they present an expressive framework for specifying probabilistic models, which has been used in several applications, such as randomized algorithms, machine learning, security, and so on. And recent years have seen the development of many probabilistic programming languages, and designing formal methods for their analysis has also become an active research topic. In particular, many of the works on formal methods also extend probabilistic programs with non-determinism in order to allow modeling unknown user inputs or over-approximating parts of the program that are too complex for formal analysis. And in this work, we also extend probabilistic programs with non-determinism. I will not talk much about it to simplify the notation for this presentation, but I do note that our method supports general non-determinism. So let me give an example of a kind of probabilistic program that we consider in this work. So this program has two variables, x and y. Consists of a double nested loop. The outer loop is executed as long as y is non-negative, and then in every outer loop iteration we set x to be equal to y, and then in the inner loop we decrease x in expectation by 1 as long as x is non-negative. Now here decrease has also a noise term, which is each time sampled independently from the standard normal distribution. And then once this inner loop terminates, we decrement y by 1. Given a probabilistic program, an almost sure termination problem asks, does the program terminate with probability 1? Or, in the presence of non-determinism, does it terminate with probability 1 with respect to every possible scheduler used to resolve non-determinism? And perhaps of all properties of probabilistic programs, almost sure termination has received most attention in formal methods literature. One of the reasons being that it is a necessary property for the correctness of many inference algorithms in probabilistic programs. There are several classes of approaches to almost sure termination analysis, and one class are those approaches based on ranking supermartingales, or RSMs. RSMs were introduced in this CAF 2013 paper, and they present a probabilistic extension of classical ranking functions for non-probabilistic programs. Whereas instead of having the deterministic decrease between two consecutive states of the value of the function, we want the value of the function to decrease in expectation upon executing a transition in the program. And there are several one-dimensional variants of RSMs that have been proposed in the literature. And one particular advantage of this class of approaches is that they can usually be fully automated, at least their computation can be automated in programs with linear arithmetic, although some more recent works also consider automation in, say, polynomial programs. So while most works consider one-dimensional variants of RSMs, lexicographic ranking supermartingales, or Lex Rsms, were introduced in this Popple 2017 paper, and they present a multidimensional extension of RSMs. They can be thought of as a probabilistic analog of lexicographic ranking functions in non-probabilistic programs, and in general, lexicographic termination arguments present an effective approach to termination analysis because they're often more easier to compute than their one-dimensional counterparts. Because now we can use different components to rank different parts of the program, different transitions, And this, for instance, simplifies reasoning about nested loop termination, where we can use different components to rank different loops, or perhaps loops with different paths through the loop body due to conditional branching, where we can again use different components to rank different paths. And for Lex Rsms in particular, this Popple 2017 paper also proposes a polynomial time algorithm to decide the existence and to compute a linear Lex Rsm in linear arithmetic probabilistic program. Now, in order to explain the problem that we study in this work, as well as to present our contributions, I need to formally define Lex Rsms. So Lex Rsm is a multidimensional function, each component mapping program states to real values, such that for every transition in the program, there exists a component, here indexed I, which satisfies the following two conditions. So the first is that f is lexicographically ranked in expectation in the ith component upon executing tau, meaning that if we have a state at which tau can be executed, then the value of the ith component will decrease in expectation by at least 1 upon executing the transition, and the previous components in lexicographic ordering will not increase in expected value. The second component, which we call strong non-negativity, requires that the value of every component at every reachable state has to be non-negative. And now observe that this is a discrepancy compared to lexicographic ranking functions in non-probabilistic programs. So there we only require those components that are actually used to lexicographically rank some transition outgoing from a state to be non-negative. And a natural question here is this strong non-negativity a limiting condition in practice? And if so, can we relax it? So I will present two examples, which actually illustrate two classes of examples, where indeed this strong non-negativity is too restrictive. So the first example is our example from the second slide, and I will show that this program does not admit a linear Lex Rsm. Here I talk about linear because these are the Lex Rsms whose computation we can automate. So in order to rank the inner loop, we would require a linear expression which involves a strictly positive multiple of x. Indeed, this will be non-negative prior to executing the transition, and it will be ranked in expected value. However, due to this decrease involving a normal distribution which has unbounded support, the value of x upon termination of the in loop can be arbitrarily negative, meaning that it is not possible to impose that this component will be negative throughout the whole program. And due to strong non-negativity, it means that we cannot find a linear Lex Rsm in this example. And this actually illustrates a more general limitation. So linear, at least, Lex Rsms are not suitable for programs with unbounded support probability distributions. And given that, for instance, normal distribution is one of the most commonly seen distributions in probabilistic modeling, this is a limitation from the practical point of view. Now, our second example does not involve unbounded support probability distributions. It's a single loop which is executed as long as x is non-negative. In every loop iteration, if y is non-negative as well, we take the if branch which decrements y in expectation by sampling the decrement from this uniform distribution. In the else branch, we decrement both x and y in expectation. And again, in order to rank the if branch, we would need an expression which involves a strictly positive multiple of y. However, the else branch can make this expression arbitrarily negative. Therefore, due to strong non-negativity, this program does not admit a linear Lex Rsm. So we can show that strong non-negativity is indeed a limitation in practice, and in this work our contributions are twofold. So first, we present generalized Lex Rsms, or G-Lex Rsms, that relax the strong non-negativity condition. And second, we propose two polynomial time algorithms for the automated computation of linear G-Lex Rsms in linear arithmetic probabilistic programs. Here, linear G-Lex Rsm means that every component at every location is given by a linear expression. And while I will explain later why we have two algorithms, I will for now note that our algorithms prove almost sure termination of these two motivating examples that I presented in the previous slides. So let me now define generalized Lex Rsms, or G-Lex Rsms. So again, G-Lex Rsm is a multidimensional function such that for every transition there exists an index I, which now satisfies three conditions. So the first is lexicographic ranking and expectation in the ith component, which is the same as before. The second now requires that at each state at which transition tau can be executed, only the first I components that actually participate in lexicographic ranking need to be non-negative. So we call this partial non-negativity. And finally, we require another condition, which we call expected leftward non-negativity, which imposes that if we have a state from which tau can be executed, and now we consider any of the first I components, let's say component J, and we consider the set of all subsequent states that we can reach by executing tau, in which the next transition will be ranked by components strictly less than J, then the expected value of Fj, when integrated over this subset of states, needs to be non-negative. Now, this is a slightly more complicated condition, so to illustrate it, I will also explain why it is necessary. So it turns out that G-Lex RSMs without this condition would not be sound, which is slightly surprising given their non-probabilistic counterpart in lexicographic ranking functions. So this example involves a loop which is iterated as long as the variable y is non-negative, and then in every loop iteration we set the probability parameter p to be 1 over 2 to the t plus 2, we toss a coin with bias p. If we get heads, we decrement y by 2 over p. If we get tails, we increment y by 1 over 1 minus p. And then we increment t by 1. Now, if you consider a one-dimensional function given just by component y, it is non-negative, it decreases in expectation. Therefore, it would be, let's say, a fake G-Lex RSM without expected leftward non-negativity. However, this program is not almost surely terminating, because for it to ever terminate, we need to take the if branch at least once. And by summing these probabilities, you can actually see that the probability of this ever happening is strictly smaller than 1. What goes wrong? Because of this if branch allowing very high decrease, we can actually take the else branch with very high probability and still satisfy the expected decrease condition. Now, how does expected leftward non-negativity prevent this? It requires that the expected value of y, when integrated, so in this case we only have one component, so we only consider terminal states at which we don't rank anything, but everything of strictly smaller component. So when we integrate y over the set of all terminal states, this integral has to be non-negative. And in this case, it's just negative values of y, so clearly this doesn't hold. And you can actually check that no matter what positive multiple of y you take and add a constant, this still wouldn't work. So expected leftward non-negativity really is necessary to make G-Lex RSMs sound. Okay, so we have defined G-Lex RSMs, which relax the strong non-negativity condition of Lex RSMs. The question is, can we automate their computation? And similar to previous work, we consider linear arithmetic probabilistic programs, and we want to compute linear G-Lex RSMs. To do this, we would like to follow a template-based approach that has been used in automation of other RSM-based proof rules. So we will fix a symbolic linear expression template for every component of the G-Lex RSM at every location in the program. We will collect all the defining conditions of G-Lex RSMs. We will convert them into an equivalent system of linear constraints over symbolic template variables, and by doing that, we reduce the computation of G-Lex RSMs to linear programming. And to do this conversion for lexicographic ranking and expectation and for partial non-negativity, we can use the existing techniques from the non-probabilistic world, and this can indeed be encoded as linear constraints. The challenge is, how do we encode expected leftward non-negativity? Because now it involves integrating over a subset of states. And such a condition hasn't been imposed in previous RSM-based proof rules. So to solve this challenge, we propose two algorithms. Our first algorithm supports linear programs with bounded support probability distributions. And in this case, it turns out that we may replace, without loss of generality, expected leftward non-negativity with a, in general, weaker condition, but in this case, this is without loss of generality. This weaker condition only requires that the expected value over all successive states is non-negative, and this is something that we show can be encoded by a system of linear constraints. This algorithm decides the existence and computes linear G-Lex RSMs in linear probabilistic programs and can solve our motivating example with bounded support distributions. Now, our second algorithm considers linear programs with unbounded support probability distributions. And in this case, it is no longer possible to replace expected leftward non-negativity just by this weak condition and remain sound. But we show that if we introduce another condition, which we call unbounded, and which slightly restricts the G-Lex RSM template, we can get still computation of G-Lex RSMs. And this is something that can also be encoded as a system of linear constraints. And therefore, we get an algorithm which decides the existence and computes a slightly stricter subclass of linear G-Lex RSMs, which can nevertheless prove almost sure termination of our first motivating example with normal distributions. Given that both algorithms reduce the computation to linear programming, both of our algorithms run in polynomial time. With this, I would like to conclude. So in this work, we propose generalized Lex Rsms, or G-Lex RSMs, which relax the strong non-negativity condition of Lex RSMs, which we demonstrated on 2 examples to be restrictive. We then propose 2 polynomial time algorithms for computing linear G-Lex RSM in linear arithmetic probabilistic programs. Our first algorithm decides the existence of linear G-Lex RSMs in programs in which all probability distributions have bounded support. Our second algorithm supports probabilistic programs with unbounded support probability distributions, decides the existence of a slightly stricter class of linear G-Lex RSMs, and we demonstrate that our 2 algorithms can prove almost sure termination for our 2 motivating examples. A natural future direction is to consider automation beyond linear arithmetic, because our relaxation of the expected left non-negativity really uses the fact that we work over linear arithmetic. So the question is, how can we do automation beyond linear arithmetic? Some one-dimensional variants of RSMs have already been automated for polynomial arithmetic, so it would be interesting to consider, can we also automate the computation of G-Lex RSMs in polynomial arithmetic and for polynomial programs? Thank you. I'll be happy to take any questions.
Thank you for the nice presentation and perfectly on time as well. So I don't see any questions in the chat. Let me see if there's someone that raised his hand or her hand. I don't see any hands either. So I have a question about the performance, probabilistic programs of reasonable size. So how does this work in practice? You gave examples of small examples, 1 component and everything, but if it becomes a bit bigger, how does it work?
So in general, this algorithm wouldn't be compositional, so it would be a global linear program solving. So I think it would scale to some programs of reasonable size, but because it's still linear programming. But like to huge projects, that's a question of whether it would scale. Okay, so you did not try this. Yes, it would also be another interesting direction in general for RSM-based proof rules to consider compositional approaches. A few works already consider this. Yeah. And what can you expect? So you said you want to look at this automation also for beyond linear arithmetic. So what can you expect then still of your algorithms? Will you be still able to find polynomial? I would expect so. So for RSMs, for one-dimensional ones, you can, with certain restrictions, compute still by reducing to linear programming. Okay. Or to semi-definite programming if programs are also polynomial. So the issue here would be to somehow allow similar style of automation for this expected left or non-negativity. Because I think that all other conditions, so maybe we will lose some relative completeness in computation because the computation of Lex RSMs also gets some completeness guarantees based on the fact that it works over linear arithmetic. But at least we would get something sound. So the question is really how to automatically check this integration condition with polynomial arithmetic. Yeah. So you say you will have to drop this non-negativity condition. Did I understand correctly? So I think it's impossible to drop it. So it's necessary for the proof rule to be sound. But you will need to somehow compute this integral in a smarter way for polynomial arithmetic. So now we show that we can avoid the explicit integration if we work with linear programs. But perhaps this integral can be somehow symbolically approximated in some special cases. For polynomial one. Yeah. Okay. So yeah. Okay. That seems reasonable. Okay. So well, I see no one has any other questions. So that means that your presentation was perfectly crystal clear.